Very good morning, student. So from today we are just going to start a new topic, that is a semiconductor. Now as far as semiconductor is concerned, these are the material whose electrical conductivity, it is somewhat more than that of an insulator but less than that of a conductor. Now why we have to study a semiconductor? That is the big question. Now as far as our today's modern life is concerned, it becomes comfortable, very easy, only due to inventions of a semiconductor. Remember, whatever electronic gadget we are using in our day-to-day life, a cell phone, a mobile, a laptop, television set, oven, so any electronic gadget or some complicated devices such as a satellite, communication satellite or international space station. So all these electronic gadgets, all of them, they are having something common, and that is a semiconductor. Means all of them, all the electronic gadgets, they use a semiconductor devices, and these semiconductor devices, they were made up of what? A semiconductor, and these semiconductor devices will order those gadgets to work as per our desire, to make our life easy and that of a comfortable also. So we must have to study what is a semiconductor. What is a semiconductor? Remember, as far as semiconductors are concerned, semiconductors are the material whose electrical conductivity is more than that of insulator but less than that of what? A conductor. Remember, the speciality of semiconductor is, as far as electrical conductivity is concerned, greater the electrical conductivity means that material is called as good conductor of electricity. So those material whose electrical conductivity is very, very small, they are called as what? Bad conductor or insulator. Whereas semiconductors, their electrical conductivity is more than insulator but less than that of what? A conductor. So what is the special thing about a semiconductor? Remember, as far as semiconductors are concerned, we will have a direct control on the various electrical properties of semiconductor. Means you can control the electrical conductivity of a semiconductor. Means if I had a conductor, insulator and that of a semiconductor, this is a conductor, this is suppose an insulator, and here it is a semiconductor. As far as materials are concerned, if given material is conductor and if I just allow the electric current to enter into the conductor, it will pass through the conductor and we will get electric current on other side. Or if I allow the current to enter the conductor from this direction, it will pass through conductor, entire current will pass through conductor and can be obtained on this side. Or if this is an insulator and if I try to enter the electric current from this end, no current can pass through it, means no current will be received on the other end. Or if I just try to enter the current from that end, even in that case no current can pass through insulator and we won't get any electric current. Means we are having two types of material. One allows the electric current, full electric current to pass through it in any direction. Other doesn't allow any electric current to pass through them from any direction. But as far as semiconductors are concerned, the electrical conductivity of semiconductor, it can be controlled. You can change the electrical conductivity of semiconductor as per your requirement, as per our desire. The electrical conductivity of semiconductor can be changed by changing the electronic configuration of semiconducting materials. So the speciality of semiconductor is that you can have a direct control on the electrical conductivity of semiconductor. Means you can tailor the electrical properties of semiconductor. Means the amount of electric current, you may allow an electric current to enter into the semiconductor. So what amount of current to pass through it, that can be just controlled. You can control what amount of current will appear on the other end just by changing the crystal structure of a semiconductor. So the speciality of semiconductor is that there is a direct control, or one can control the electrical conductivity of semiconductor. Remember, the electrical conductivity of semiconductor, it depends on temperature also, it will vary. Just like the electrical conductivity of conductor or insulator were changing with the changing temperature. But as far as semiconductor is concerned, its dependence of electrical conductivity on the temperature, that can also be controlled. Means you will have a direct control over the electrical properties of a semiconductor, just like electrical conductivity. Just like what? Electrical conductivity. Now, as far as semiconductor is concerned, in semiconductor only it is possible what fraction of current to pass through it, in which direction that current is allowed to pass. Suppose I will enter the current from this direction, from this end. Then, as far as semiconductor is concerned, you can give the command to the semiconductor that it won't allow any current to pass in this direction. Means, a semiconductor can allow the flow of current only in one direction as per our desire. It will not allow the current to flow in opposite direction. It is as per our desire. Means there were so many electrical properties of a semiconductor, just like its electrical conductivity, just like the dependence of electrical conductivity on the temperature, various electrical properties that can be controlled. Number of charge carriers that can flow, means you will have a control on the charge carrier through that semiconductor. So amount of charge carrier in a semiconductor, that can be controlled just by changing the percentage of doping in that semiconductor. So remember, as far as materials are concerned, materials are classified into three categories. They might be a conductor, they might be semiconductor, or they might be an insulator. Conductor, semiconductor, or that of an insulator. Regarding semiconductor, what is the speciality of semiconductor? We will have a direct control on the various electrical properties. You can customize the electrical conductivity of a semiconductor. What you can say? Electrical conductivity, which is denoted by sigma. So, electrical conductivity of a semiconductor, that can be controlled. That can be controlled as per our desire or as per our requirement. Means number of charge carrier that flows through the semiconductor, that can be controlled. As far as conductors are concerned, in a conductor, large number of free electrons are available. Large number of free electrons are available for the conduction of electric current. Whereas as far as insulators are concerned, no free charges are available for the flow of electric current, or the number of free electrons available for the conduction of an electric current, they are very less as compared to that of number of free electrons available for the flow of electric current in case of a conductor. So materials are broadly divided into three types. Before the inventions of semiconductors, materials are either conductor or materials are either an insulator. Now, as far as conductors are concerned, what you can say? All the metals are good conductors of electricity. All the metals are what? Good conductors of electricity. As far as insulators are concerned, what you can say? A glass or a wood or a plastic or a rubber, they are all examples of insulator. Now, as far as semiconductors are concerned, germanium and silicon, these are the popular elemental semiconductor. Now, as far as conductors are concerned, if I just measure the electrical conductivity of a typical metal, metals are good conductors of electricity, and the electrical conductivity, which is denoted by a symbol sigma. So, the electrical conductivity for a metal like silver, it is of the order of 6.25 into 10 to the power 7, and the unit of conductivity is Simon per meter or Simon meter inverse. As far as insulator is concerned, if I just measure the electrical conductivity of an insulator like glass, that electrical conductivity of glass, it is 10 to the power minus 10 Simon meter inverse. See, the conductivity is very, very small, 0.00000001 Simon meter inverse. Now, electrical conductivity of silicon is measured. It is found to be nearly 1.56 into 10 to the power minus 3 Simon meter inverse. So, here I have taken some examples of electrical conductivity. I had measured the electrical conductivity of silver, conductivity of what? Electrical conductivity of silicon and that of glass. And what conclusion I can draw? That the electrical conductivity of semiconductor, which is 1.56 into 10 to the power minus 3. So, the electrical conductivity of a material which is a semiconductor, it is more than that of electrical conductivity of insulator, but it is less than that of what? The electrical conductivity of metal. So, the material whose electrical conductivity it lies in between conductor and that of insulator, they are called a semiconductor. So, in short, what you can say? A material whose electrical conductivity it lies in between insulator and that of a conductor is called semiconductor. That is, conductivity of semiconductor is more than that of insulator, but it is less than that of what? A conductor. It is called as a semiconductor. Now, let us see that as far as electrical conduction in a solid is concerned. Now, you had already studied that the electrical conductivity of solid. What is the formula for electrical conductivity of solid? Electrical conductivity of solid, it is denoted by a symbol sigma. What sigma represent? Sigma represent the electrical conductivity of a solid, and that electrical conductivity sigma is equal to NQ into mu. Electrical conductivity of solid, it is given by formula sigma equal to N into Q into mu. Now, here what N represent? N represent charge carrier density. N is known as charge carrier density. Now, what is charge carrier density? Charge carrier density is nothing but number of charge carrier present per unit volume. Number of, what you can say? It is number of charge carrier, number of charge carrier per unit volume, number of charge carrier per unit volume. It means it is a number charge density. In other words, you can say N is also defined as number charge density or charge carrier density or number of charge carrier per unit volume. Means electrical conductivity, it depends on how many number of charge carriers were present per unit volume. Second thing, the electrical conductivity depends on the charge on carrier. Charge on carrier. Q represent what? The net charge on that carrier. The electrical conductivity also depends on the mobility of charge carrier for a given material. What do you mean by a mobility? Mobility is nothing but it is the measure of how is the charge carrier in a material can move, how easily the charge carrier in a given material will move in presence of external magnetic field. Remember what I am saying? Mobility, if I say this is a material and I want to measure the mobility of a material, then I will apply an electric field. That electric field will be pointing like this. And the charge carriers, which are the electrons, they are moving in opposite direction. So the measurement of mobility of a given material is nothing but measure of how easily the charge carriers they can move within the material in presence of an external magnetic field, in presence of an external electric field, in presence of what? External electric field. Remember, the mobility will be decided, or it will depend on so many factors. It depends on what is the mass of charge carrier. What is the mass of charge carrier? It depends on the material, whether that material is crystalline in structure or whether that material is amorphous in nature. It depends on the type of defect in that crystal. It depends on the type of defects in the crystal. It also depends on, as far as electrical conductivity is concerned, it also depends on the temperature of that material. So remember, as far as electrical conduction in a solid is concerned, electrical conduction in a solid is concerned, it is given by formula electrical conductivity sigma equal to N into Q into mu. So electrical conductivity of a solid or a material, it depends, number one, on temperature. It depends on charge carrier density, that is number of charge carriers per unit volume. It depends on the net charge on a carrier. It depends on the mobility. Mobility means the ability of charge carrier, that how easily they can move within the material in presence of an external magnetic field. And this mobility depends on the mass of charge carrier. This mobility depends on whether that material is crystalline in structure, whether that material is what? Amorphous in nature. It also depends on the type of defect in a crystal. It also depends on the type of, the amount of impurity atom added to that crystal. Amount of impurity atom added to that crystal, that will also change the electrical conductivity of a solid. Electrical conductivity of a solid. So, depending upon the electrical conductivity, solids can be classified, or the conductors can be classified into three categories. Number one, either they are conductor. Number two, or they are insulator or bad conductor. And number three, either they are neither a conductor nor an insulator, they are what? A semiconductor. So depending upon the electrical conductivity sigma of a material, depending upon the electrical conductivity, what is electrical conductivity? Sigma, that is NQ into mu. Materials are classified into three categories. Either a material is a good conductor, or a material, it may be what? An insulator. Insulator means bad conductor, or it may be a semiconductor. So remember, depending upon the electrical properties of a material, all the materials, they are classified, they are divided into three categories: conductor, insulator, and that of a semiconductor. Now, as far as conductors are concerned, what you can say? All the metals are good conductors of electricity. While the examples of insulators are what? Glass or wood, or what? Glass, wood, rubber, plastic, they are all the examples of insulator. and you know very well the elements belonging to fourth group of periodic table, just like germanium or silicon, they are the popular semiconductors. So all the metals are good conductors of electricity, all the insulators are bad conductors of electricity, and the material like germanium and silicon whose electrical conductivity is in between the electrical conductivity of what? Conductor and insulator, they are called as a semiconductor. They are called as what? A semiconductor. Remember that as far as electrical conductivity of a material is concerned, basically it depends on the availability of charge carrier density, means how many number of free electrons are available per cubic meter. Number of free electrons present per cubic meter will decide the electrical conductivity of a material. Now, as far as concept of free electron is concerned, if I just consider an isolated atom, what isolated atom consists of? That every atom has a centrally situated massive region called as a nucleus, which contains positively charged particles like proton and electrically neutral particles like neutron, and the negatively charged particles, that is electrons, are revolving around the nucleus in different circular orbit. Now if I just consider the electron in the outermost orbit as compared to electron in the innermost orbit, we know that electron in the innermost orbit, they are strongly bound with nucleus, whereas electron in the outermost orbit, they are loosely bound with nucleus. And as far as solids are concerned, in a solid, atoms are closely packed. Atoms are closely packed. As far as an isolated, that is a single atom is concerned, this electron is having interaction with the nucleus of this atom only. And as far as this electron in the outermost orbit is concerned, those electrons which are lying in the outermost orbit, you know very well that electron in the different orbits, they will have different energy level. In case of hydrogen atom, we know that electron in the innermost orbit having principal quantum number n is equal to 1. What is the energy of electron? Minus 13.6. In the second orbit, minus 13.6 divided by 4. In the next orbit, minus 13.6 divided by 9. Means electron in the outermost orbit means that electron is lying in what? The higher energy level. Energy level of electron in the outermost orbit is high. So these electrons, they are loosely bound with nucleus, and in solid, electron atoms are closely packed. Closely means what is the interatomic spacing? The distance of separation between the two atoms in a solid, it is of the order of 2 to 3 angstrom. Angstrom means 10 to the power minus 3, means that distance will ranging from 2 into 10 raised to minus 10 to 3 into 10 to the power minus 10. So you can imagine they are so close to each other, so that here the orbits of atoms, they will overlap. Due to overlapping of the orbit, the electrons in the outermost orbit, already they are loosely bound with this nuclei. Now these electrons in the outermost orbit, they are having what? A very large interaction. This electron has interaction with the nucleus of its own atom, nucleus of the neighboring atom also. This electron will interact with the electrons in the neighboring atom also, means this electron will exert a force of repulsion. This nucleus of second atom will exert a force of attraction. Here there is another atom whose nucleus will exert a force of attraction, means electron in the highly energetic orbit or electron in the outermost orbit, they have a strong interaction with the nucleus as well as electrons of neighboring atom, and due to which the energy level of that electron will change, and that electron which is initially revolving in the orbit of a given atom, now that electron it can revolve in the orbit of the neighboring atom also. So as far as those electrons which are lying in the outermost orbit and which are loosely bound with the nucleus in a solid where the atoms are very close to each other, so the electrons in the outermost orbit, they will have a strong interaction with the nucleus of neighboring atom as well as with the electrons in the neighboring atom, and as a result of which these electrons, they are free to move in the outermost orbit of one atom to that of other atom within that material. So those electrons which are lying in the outermost orbit, which do not satisfy the condition required for stable electronic configuration and which are free to move within that given material, they are called as free electron, and depending upon how many number of free electrons are present, remember, number of free electrons per unit volume, N represent what? Sigma is equal to N Q mu. N represent charge carrier density. Charge carrier density means number of free electrons per unit volume, number of charge carriers per cubic meter, means how many number of free electrons are available in a cubic meter, in a 1 cubic meter of volume. That is nothing but charge carrier density, and the value of this charge carrier density will decide the electrical conductivity. So remember that materials are classified into 3 categories, and if I just consider the conductor, those materials which are good conductors of electricity, they are all metals. And as far as a typical metal is concerned, if I just count that a typical metal has 10 to the power 28 number of free electrons per cubic meter. This much number of free electrons are there in a 1 cubic meter of a volume. So number of free electrons per cubic meter in case of typical metal, it is 10 to the power 28. It means electrical conductivity of conductor is very large, because large number of free electrons are available for conduction of electricity. So those material which consist of large number of free electrons per cubic meter which is made available for conduction of electricity, they are called as good conductors of electricity. And for a typical metal, here number of free electrons per cubic meter, it is in the range of 10 to the power 28. Now as far as insulators are concerned, it has very less number of free electrons per cubic meter, 10 to the power 23 per cubic meter, means a number of free electrons available per cubic meter, number of free electrons available per cubic meter in an insulator is very small, that is of the order of 10 to the power 23 per cubic meter as compared to that of number of free electrons per cubic meter in case of conductor. So if I compare this 10 to the power 23 number of free electrons per cubic meter with 10 to the power 28 electrons per cubic meter, this number is negligible. This number is what? Negligible. And as far as semiconductors are concerned, what you can say? The number of free electrons per cubic meter in a semiconductor, it is more than that of insulator, but it is less than that of what? A conductor. More than that of insulator, but less than that of a conductor. So how many number of free electrons are available per cubic meter in a semiconductor? That we can decide, that we can change as per our desire, depending upon what amount of impurity atom either from 5th group of periodic table is added as a impurity, or whether it is a donor type impurity or whether it is what? An acceptor type of impurity. So remember one thing, that as far as semiconductors are concerned, number of free electrons per cubic meter in a semiconductor, definitely they are more than that of insulator, but they are less than that of what? A semiconductor, but they are less than that of semiconductor. Now the examples of semiconductor, germanium, silicon. In addition to this germanium and silicon, what you can say? Gallium or gallium arsenide, gallium arsenide, again gallium nitride, or it may be a cadmium sulfide. Examples of conductor: any metal, aluminium, copper, silver. Examples of insulator: glass, wood, rubber, plastic. Examples of semiconductor: germanium, silicon, gallium arsenide, gallium nitride, or cadmium sulfide. The electrical conductivity of typical metal is sigma is equal to, means the electrical conductivity of silver, it is 6.25 into 10 to the power what? 6.25 into 10 to the power 7 Simon meter inverse. The electrical conductivity of insulator, it is in the range of 10 to the power minus 10 Simon meter inverse. The electrical conductivity of silicon, it is in the range of 1.56 into 10 to the power minus 3 Simon meter inverse. Simon meter inverse. So, the speciality of semiconductor, that we have to remember, that the number of charge carriers per cubic meter in a semiconductor, that we can control as per our requirement, as per our desire. So, as we can have a direct control on the electrical conductivity of semiconductor, so that's why semiconductor has large number of application in electronics industries. And by using this application, that is, you can alter, you can tailor the electrical conductivity of semiconductor as per your desire. So that's why those semiconductors, they can be used in large number of electronic gadgets. It may be used in what? It may be used in our cell phone, it may be used in our smartwatches, it may be used in any electronic gadget in our house. Some of the complicated applications of semiconductor and its devices, it may be used in what? Satellite, which is used for the purpose of communication, and various military applications, various weather forecasting applications. Remember, semiconductors were also used in what? The space stations. Space stations also. Now, as far as semiconductors and conductors are concerned, they will have their electrical conductivity. It has a dependence on temperature. Already electric current through the conductor. In that topic we had seen how the electrical conductivity of conductor will changes as per temperature. If you remember that a graph is plotted between the temperature against the electrical conductivity. So electrical conductivity, it is denoted by sigma. So here we will try to plot the graph of variation in the electrical conductivity, variation in electrical conductivity versus temperature. So first we will plot a graph for a conductor, and then we will try to plot a graph for a semiconductor, and we will see what is the difference between the two graphs. So as far as conductors are concerned, the conductivity of conductor, no doubt it depends on temperature, and what we will observe, that the electrical conductivity of conductor will vary with temperature as per this graph. And what you can say here, look at this, when temperature is less, conductivity is more, when temperature is more, conductivity is less. Means as temperature goes on increases, electrical conductivity of conductor goes on decreases. So what is the relation? In case of conductor, in case of a conductor, the electrical conductivity of conductor goes on decreases with increasing temperature. Means they are inversely proportional. Sigma is inversely proportional to temperature, exponential decay. This curve is what? Exponential decay. Whereas in case of semiconductor, graph will be of this type. And what you can say here, when temperature is small, conductivity is small. As temperature goes on increases, conductivity will goes on increases. Means, as far as semiconductors are concerned, the conductivity of semiconductor goes on increases with increasing temperature. Means, behavior of electrical conductivity of semiconductor is different than that of behavior of electrical conductivity of a conductor. So, the variation in the electrical conductivity of semiconductor with variation in temperature, that can also be controlled. That can also be controlled. So, remember, we are having basically three different types of semiconductor depending upon whether they are element, whether they are compound, or whether they are some organic material. So, semiconductors are of three different types. Semiconductor are of three different types. The first type of semiconductor, they are known as elemental semiconductor. The first type of semiconductors are known as what? Elemental semiconductor. What are the examples of elemental semiconductor? The elemental semiconductors, they are actually the elements like what? Germanium and that of silicon are the examples of what? Elemental semiconductor. The second type of semiconductor, which are actually formed by the compound. So, they are called as a compound semiconductor. They are called as what? A compound semiconductor. What are the examples of compound semiconductor? Cadmium sulfide and zinc sulfide. Cadmium sulfide and zinc sulfide are the examples of compound semiconductor. And the third type of semiconductor, they are organic semiconductor. As far as this third type of semiconductor is concerned, they are newly invented. So, that's why organic semiconductor till today there has less application in our day-to-day life, but in a short duration of time, the invention of organic semiconductor may have large number of application in electronics industries. So, examples of organic semiconductors are anthracene, and the second example is polyaniline. Because these are related with chemistry. Those who are the student of chemistry, they know very well. Anthracene and that of polyaniline, these are the examples of organic semiconductor. Remember, elemental semiconductor and compound semiconductor, they were invented earlier. So, they had what? Large number of application in electronics industries. As far as cadmium sulfide, zinc sulfides are concerned, they are what? Photosensitive material. So, that's why as far as photocells are concerned, the inner surface of emitter is coated with thin layer of photosensitive material like cadmium sulfide. So, they are having applications in various electronic gadgets. And organic semiconductor, because they were already invented newly, so they had what? A limited application in today's electronic industries. Remember, as far as semiconductors are concerned, the electrical conductivity of semiconductor can be controlled as per our desire. What I am saying? The electrical conductivity of semiconductor, it can be controlled as per our desire, and the electrical conductivity of semiconductor, they are different than that of a metal and different than that of a conductor and that of insulator due to their unique conduction mechanism. Semiconductors are having what? Unique conduction mechanism. They are having what? Unique conduction mechanism. See, as far as semiconductors like germanium or that of silicon is concerned, both germanium and silicon, they belongs to fourth group of periodic table, means they are tetravalent. Means they are what? Tetravalent. Means their valency is 4. It means they are having 4 electrons in their outermost orbit. If I just say this is the nucleus of germanium, how many free electrons are available in its outermost orbit? This germanium atom has 4 free electrons in their outermost orbit, and those electrons they are called as what? Free electrons or valence electron. Now, if germanium has only 4 electrons in its outermost orbit, means they do not satisfy the condition required for stable electronic configuration. In order that germanium atom to become stable, it must have 8 electrons in its outermost orbit, or otherwise germanium atom is highly unstable. So as far as the crystal of germanium is concerned, we know that a crystal of germanium, let us consider these are the nucleus of the neighboring germanium atom. So here I had considered the 4 neighboring germanium atom, their nucleus are present. Now each of these germanium atom, they are having 4 electrons in their outermost orbit. 4 electrons in their outermost orbit. So as far as the centrally situated germanium atom is concerned, to make it stable, it needs 4 more electrons. So every germanium atom, it will share 1 electron of this germanium atom, 1 electron of this germanium atom, 1 electron of this germanium atom, and 1 electron of this germanium atom. So because the semiconductors like germanium, which belongs to 4th group of periodic table, means they are tetravalent, so their valency is 4. So in a germanium crystal, every germanium atom, they become stable by sharing 1 electron each from 4 of its neighboring germanium atom, by forming what? Here there will be a formation of strong covalent bond. Remember, as far as these covalent bonds are concerned, these bonds are strong if temperature of semiconductor is absolute 0. Means at absolute 0 temperature, every germanium atom in a germanium crystal, it becomes stable by sharing 1 electron each from 4 of its neighboring germanium atom by forming 4 strong covalent bonds. But as temperature increases, few of these covalent bonds they becomes loose, and thereby few electrons they are available as a free electron. Means conductivity of semiconductor will increases with increase in temperature, means at room temperature, because few of the covalent bonds they becomes loose and few free electrons are available for conductivity. So that's why at normal temperature or at room temperature we are having few charge carrier in a semiconductor, which can be used for what? For the purpose of electrical conductivity. So you remember that semiconductor, the electrical conductivity of semiconductor, why it is different than that of conductor and insulator? Due to what? Its unique conduction mechanism. And to know the unique conduction mechanism of a solid, we must study that band theory of solid or band theory of crystal.